Section 5 is all about logic and reasoning. Now there are two kinds of reasoning we're going to look at, inductive reasoning and deductive reasoning. Inductive reasoning is only likely true. It's not always going to be true, but sometimes it can help out. Deductive reasoning is definitely true, and this is the one we're going to be studying a little more closely. Most of what we're going to be working with is deductive reasoning. Now, inductive reasoning, being that it is just likely true, this is how it works. It uses observations or trends to make a rule. You're using facts that you know or observations to create a rule about something. So if the facts are, I checked 10,000 dogs and 10,000 dogs and they all had fleas, I would make a rule then that all dogs have fleas. Now, you can tell in my example, that's definitely not true. The rule that I made is wrong. Even though it makes sense to make that rule based on this observation that all of them have fleas, well, not all dogs have fleas. So my rule is incorrect. So this is just a way to show that inductive reasoning doesn't always work. Now mine is kind of an extreme example, but again, that's just to kind of illustrate or show that it doesn't always work. Deductive reasoning, on the other hand, does always work. You're using known facts to make more facts. If inductive reasoning takes facts and makes a rule, deductive reasoning takes rules to make facts. So, if the rule is that red meat has iron in it. Iron is a mineral that our body needs. We need it in our diet, helps with our blood, things like that. So, you want to get some iron, and we know that red meat has iron. As a rule, this beef that I'm about to eat is red meat. So, two rules. Therefore, I can make the fact, therefore, this beef has iron in it. Even without checking this hamburger that I'm about to eat, I can say this beef has iron in it because of these two rules. Red meat has iron, this beef is red meat, therefore, this beef has iron. So inductive reasoning, facts make rules, doesn't always work. It is likely true, but not always. Deductive reasoning, rules make facts. This is definitely true. So again, we're more than likely we'll be sticking with deductive reasoning. Conjunctions and disjunctions. These are different statements that you can say about different things. So over here, for our example, we have a Venn diagram with a bunch of different numbers. Now, in this circle, we're looking at only even numbers. Now, obviously, this is not every even number there is. This is just some of them. In this circle, we are looking at multiples of 3. Again, not every multiple of 3, just some of them. Outside, obviously, then, would be all of the numbers that are not even numbers and are not multiples of 3. Inside this portion would be numbers that are both even and multiples of 3. So a conjunction is a compound sentence or statement that uses and. Both statements must be true for the conjunction to be true. So if we are looking at even numbers and multiples of 3, a conjunction would be numbers that are even and multiples of 3. So the conjunction would just be this area. For example, we can say 6 is even and 6 is a multiple of 3. That is a true conjunction. Both of these statements are true, so this conjunction is a true statement. I can say another thing. The sky is blue and gasoline is flammable. Well, again, because this statement uses and, meaning that both things have to be true, well then this is a true conjunction, because today, at least for me, the sky is blue, and gasoline is also flammable. Both of these are true, therefore this whole statement, this conjunction, is true. On the other hand, a disjunction is a compound statement that uses or. Now, because of the fact that it uses or, it just means at least one of the statements must be true for the disjunction to be true. They don't both have to be true, or you don't need all of the statements. I suppose there could be more than two things in there. You just need one thing to be true for the disjunction to be a true statement. So a disjunction would be everywhere in this circle and in this circle, or this piece in the middle. any of these numbers would be a disjunction of even numbers and multiples of 3. So 2 is even, or 2 is a multiple of 3. Well, 2 is not a multiple of 3, so that part is false. But 2 is even, so this whole statement is a true disjunction, right? Because we can see this part is in fact correct. Now, if I changed it and said odd, 2 is odd, or 2 is a multiple of 3. This statement is still a disjunction because it uses or, but it would no longer be true. It would be a false disjunction. Oops. So it would still be a disjunction. It would just be false. Another example, the sky is blue or today is Saturday. Well, for me, both of these statements, well, this whole statement, I should say, is true. The sky is blue today, but today is actually Wednesday. So even though this part is false, again, this whole statement as a disjunction is a true disjunction because today the sky is blue. So we are going to form conjunctions and disjunctions from other statements. If we're using the statements pi is an irrational number, which by the way, that is true. Pi is probably the most common irrational number. We're also going to use the statement 4 is a factor of 30. Well, that one is false. 4 does not go into 30. 4 would go into 28, and then 4 would go into 32, but not in the middle there. 4 does not go into 30, so that's a false statement. So we're going to create a conjunction saying pi is irrational and 4 is a factor of 30. This is a conjunction statement. But this conjunction statement is false. It is false because not both of these statements are true. 4 is not actually a factor of 30, thus our conjunction that we made is actually false. I'm going to make a disjunction then by instead of saying and, I'll just say or. Pi is irrational or 4 is a factor of 30. Well, this is true, since at least one of the statements is true. This first part is actually correct. Pi is irrational, but again, 4 is not a factor of 30. So true part, false part, but since it's an or, technically this whole statement is correct. All right, we're going to look at conditionals now. A conditional is just a statement, compound statement, formed by combining two sentences, statements, or facts using the words if and then. Sometimes you'll hear it called an implication. Sometimes you might just call it an if-then statement. So, for example, if it is raining outside, then Mr. Rogers will carry an umbrella. Well, that's a conditional. Here's our condition. Here is what happens. If it happens to be raining outside, then Mr. Rogers will do something. He'll carry an umbrella. So if this condition is met, then this will happen. That's what makes a conditional. Now there are different pieces of a conditional statement. There's the if part and the then part. So in the conditional statement, the phrase or the statement after if is what's called the hypothesis. So when we read, if it is raining outside, then Mr. Rogers will carry an umbrella. This part, the if it is raining outside, the it is raining outside is called the hypothesis. It's just the condition that needs to be true for the rest of the statement to become true. The conclusion, on the other hand, then, is the then part of the statement. If it is raining outside, then Mr. Rogers will carry an umbrella outside. This part of the sentence, Mr. Rogers will carry an umbrella outside, is what's called the conclusion. So every conditional is made with a hypothesis and a conclusion. If this is true, then this will be true. Now, it doesn't always have to be that the hypothesis comes first. You just have to think in your mind which part is the if statement, which part is the then statement. So when we say this statement, a figure has 4 sides, if the figure is a square. Well, what piece comes after the if? The hypothesis is this piece. The figure is a square. The conclusion, then, is that it has 4 sides. if the figure is a square, then it has 4 sides. So you can technically write it so that the hypothesis is at the end with a conclusion at the beginning. You just, again, you have to think, where is my if? Where is my then? Logical notation. This is just a different way of writing our statements. A lot of times you might see it written this way. There's a P, arrow, Q. You would read this as if P, then Q. Or every P is a Q, P implies Q, P only if Q. Basically what this is saying is P is our hypothesis and Q is the conclusion. If P is true, then it means that Q will be true. It's just a different way of writing it. A counterexample. A counterexample is a way of, or it's another kind of statement that comes from a conditional. It's a way of proving it false. All you have to do is just, you can prove the whole thing wrong by giving an example that doesn't work. So, for example, if I say, if an animal swims, then it is a fish. This is a conditional statement. My hypothesis, an animal swimming. My conclusion, that animal is a fish. Well, a counterexample is, well, look, there's a dog swimming. Obviously, we know it is an animal swimming, the animal that swims, but it is a dog. It is not, in fact, a fish. So I can make this counterexample to prove that this conditional is false. A converse. A converse is just a different way of writing your conditional. The converse of a conditional is the hypothesis and the conclusion flipped around. Now, the converse is not always true, even if the original conditional is true. So, for example, if my original conditional statement says, if it is raining, then Jack eats macaroni. Maybe Jack just gets really sad on raining days, and his happy food is he eats macaroni. But macaroni, maybe that's also his Monday foods. So every Monday, Jack will eat macaroni, even if it isn't raining. So the converse statement says, if Jack is eating macaroni, then it is raining. So notice, all we did was flip around the it is raining and Jack eats macaroni. We just flipped those two pieces around, made this a if statement instead of a then statement. So we can say that this one is absolutely true. If it is raining outside, then Jack eats macaroni. The converse isn't necessarily true, because if it says, if Jack is eating macaroni, then it's raining, well, that's not true. It could also just be a Monday, and he wanted to eat it. So, if your original statement was P implies Q, or if P, then Q, the converse of that statement would be written this way, if Q, then P. So, again, going back to the notation, converse is just written by flipping those two statements. And again, remember, converse isn't always true. So let's look at some examples of these. Looking at the statement, the sum of the measures of a rectangle is 360 degrees. We need to write this implication in the form if P then Q. So the if statement is if a figure is a rectangle, then the sum of the measures of the angles is 360. If, then. Okay, again, we didn't actually see up here the words if and then, but you need to kind of read between the lines and figure out this is basically saying if it is a rectangle, then the sum will be 360. What is the hypothesis? Well, the hypothesis is that the figure is a rectangle. What's the conclusion? The sum of the measures is going to be 360 degrees. Is this a true or false implication? We haven't necessarily gone over this yet. You may have learned this in previous classes, but yes, this is actually true. Any rectangle that you come across, if you measure all of the angles inside, there will be 4 angles, each of them 90 degrees, and so they'll add up to 360. So this is a true implication. What is the converse of this statement? The converse says if a figure's measures sum to 360, then the figure is a rectangle. Now it doesn't ask us that, but we can also ask the question then, is that true or false? Technically this is false. There are a lot of other figures that if you add up all of their angles will come to 360, and they don't have to be rectangles. Just to do one example, let me see if I can find it. This one right here. If I make this trapezoid, again, if I were to measure each one of these angles and add them all up, this would come to 360 degrees. Again, this is not a rectangle. So even though if it's a rectangle, the sum will be 360, this is true. The other way around isn't true. If it adds to 360, like this does, then it is a rectangle. Well, this is not. This would be my counterexample. Let's look at another example then. We're going to rewrite each implication in an if-then form, and then say whether it's true or false. If it is false, we'll give a counterexample. Then we're also going to write the converse and say whether or not that is correct. So, if our statement says every number divisible by 5 ends in 0. So, we need to think, where is my if, where is my then? So for this one, it would say if a number is divisible by 5, then it ends in 0. Right? That's just another way of rewriting this statement in an if-then way. Technically, even though this is our correct way of writing a conditional, the conditional we wrote happens to be false. And I can give you an example, the number 15. 15 is divisible by 5, but it does not end in 0. So this statement is false. I can, again, say that because of my counterexample. We can write the converse just by flipping these around. If a number ends in 0, then it is divisible by 5. This one is true. If we wanted to show a proof of it, we'd be kind of a long, tedious proof, and we can do that later. But right now, we're just going to think of the fact that things like 10, 30, 200, 1,250, well, all of these are divisible by 10 because they have a 0, and anything divisible by 10 is also divisible by 5. So the converse is true, but in this one, the original statement actually isn't. Again, we're going to rewrite the implication in the if-then form. So, cats are 4-footed animals. If an animal is a cat, then it has 4 feet. Right? It's basically the same way, well, it's the same statement, just written in a different way. Cats are 4-footed animals. If it is a cat, then it has 4 feet. This is actually true. If an animal is a cat, it is supposed to have 4 feet. I know some of them don't. They might have been born with a disfigure, or they might have lost it somehow, but we're going to say in general, this is a true statement. Let's look at the converse, though. If an animal has 4 feet, then it is a cat. Well, again, that's not necessarily true. Okay, just because this one is true doesn't mean that this one is true. It could be a dog, it could be a giraffe, it could be a bear. There are a number of different things it could be. Doesn't have to be a cat. So again, this is just kind of a few examples of logic and reasoning.